In this video, I'm going to discuss where a function is either increasing or decreasing from two different points of view. First, when a function is given as a graph, and then when a function is given as a formula. So this is an example of the kind of graph that you'll see in the problems on Hawks. And what we see here is the as x is increasing, here's your x-axis, here's your y-axis. As x is increasing, y is decreasing up until this point, up until x equals 0, and then it's increasing and continues after that. So a way you would provide the answer in a case like this is, even though this is the only portion of a graph that you can see, it's assumed from the arrows that the graph continues on like to minus infinity in this direction and to plus infinity in this direction. So for this particular graph, what you would specify for an answer in Hawks is the function is decreasing for this interval, so from minus infinity all the way to 0, and use parentheses. That's an open interval, so x is greater than minus infinity and x is less than 0. What we have here is a case where the derivative is negative. At this point, there's a kink in the graph, a corner, so the derivative is undefined. Then for this portion of the graph, the derivative is positive, therefore a function is increasing. So the answer that you would give for where a function is increasing in this case is 0 to infinity. So x greater than 0, less than infinity, the function is increasing. Now let's look at a situation where a function is given as a formula, in this case x plus 7 over x squared. So one of the kind of problems that you see in Hawks is it's asking where a function has horizontal tangents. So that means f prime of x, the derivative, is equal to 0. So horizontal tangents are one thing that indicate to us where a function might possibly switch from increasing to decreasing or vice versa. So we need the derivative. And for this, there's a couple ways we could do this, but in this case I'll just use a quotient rule since it's already written as a quotient. So we have the denominator x squared times the derivative of the top. The derivative of x plus 7 is just 1. Minus x plus 7, the top, minus the derivative, minus the top, x plus 7, times the derivative of the bottom, 2x, over the denominator squared, so that's x to the 4th. But this needs to be simplified, so I have x squared, and then I distribute this 2x through the x plus 7, so I have minus 2x squared plus 14x. So I have x squared minus 2x squared, so that's minus x squared, and then I have minus 14x all over x to the 4th. And you can actually factor an x out of the numerator. Actually, I'll factor out a minus x and simplify to minus the quantity x plus 14. So minus is written out here, it applies to this whole thing, over x cubed. So to see where this is equal to 0, we can just set the numerator equal to 0. X plus 14 is equal to 0, so x is equal to minus 14. And that is the only x value at which the derivative is 0. So that is the only place where we have a horizontal tangent. Now, what I'm going to do is draw a real number line here. So minus infinity and infinity. And I'm going to mark on a real number line where we have this horizontal tangent, minus 14. Okay. Now, horizontal tangents will divide the real number lines into regions where the function may be increasing or decreasing. But before we continue, we also need to note where a function is undefined, because when a function is undefined, that can also cause a function's graph to switch from increasing to decreasing or vice versa. So let's go back to the original function, and we see that the function is undefined at x equals 0 because that is where the denominator would be 0. So you need to make note of any such points where the denominator is equal to 0. So now I'll note that on the number line also. So if there are also any additional points where the derivative is undefined, those should also be noted. But if we look at their derivative here, that also is undefined at x equals 0. We've already accounted for that. So there are no new points. So, so we've divided a real number line into regions. And I'll indicate these as intervals. So minus infinity up to minus 14. And then minus 14 up to 0. And then 0 to infinity. So we have three intervals on which the function is either always increasing or always decreasing. And we just have to find out which. So I'm prepared to write down our answers. And what we're going to see is we have three intervals. So what could likely happen is it's increasing on one of them and decreasing on the other two, or vice versa. So what we can do to determine whether it's increasing or decreasing is choose any x value in each of these three regions. Like, for instance, I could choose like minus 15 or minus 20 for this region. Or I could pick like minus 5 or minus 1 for this region. And then I could pick x equal 1, for example, for this region. You can pick anything, just as long as you leave out these endpoints. It has to be something that is strictly within these three regions. So, and we choose those x values and substitute them into the derivative. So, for instance, for this region, if I choose x equal to minus 15, so f prime of minus 15 is equal to minus out front, and then I have minus 15 plus 14 over minus 15 cubed. Now, you actually don't need to necessarily work this out to a number. All you really need to do is determine whether the overall result is positive or negative. Now, the numerator, we have minus 15 plus 14, so that's minus 1, so that's negative. Here, down below in the denominator, we have a negative number cubed. That is also negative. So we have a negative or a negative, which is positive, but then we have a minus out front, which makes the overall result negative. So that prime of 15 is negative. That means that the function is decreasing on this interval. So I'll include that in my final answer. Minus infinity up to minus 14. Now, for the second interval, let's pick, say, x equal to minus 1, because that's in between minus 14 and 0. So I have minus 1 plus 14 over minus 1 cubed, but then the whole thing is negated. So the numerator is positive. We have minus 1 plus 14 is 13. The denominator is negative, just like before. But then we have the negative out front. So the overall result is positive. So the function is increasing between x equals minus 14 and x equals 0. And finally, I can choose any x value greater than 0 to plug it into a derivative, determine whether a function is increasing or decreasing in this interval. So I'll just choose 1. So that would be the minus, and I have 1 plus 14 over 1 cubed. So I have positive up top, positive down below, but I have a negative out front, so the overall result is negative. So here it was positive, here it's negative, so it is decreasing between x equals 0 and infinity. So that is your final answer. These are the intervals that you would enter in Hawks for where a function is increasing or decreasing. Notice that it alternated between decreasing and increasing. That is what often happens. However, be careful, it does not always happen. There are possibilities where your derivative is 0 at a certain point and is increasing both before and after. For instance, a function that behaves like this, a function has a horizontal tangent right here, but is increasing before it and increasing, I have to watch my graph here, and is increasing after it. So this typically happens, for example, if a function, if the first derivative and the second derivative are equal to 0 at a particular point. There's one circumstance that can cause the behavior to not change. So increasing, increasing, or decreasing, decreasing. So beware, don't be lazy about this. It does not always alternate. You have to check each region.